Good day, everybody, and welcome to 24 Hours of Patch. Getting towards the tail end of the sessions now, and we've got a great one lined up for you here. Brandon Leach's session, where we'll be talking about data pages, allocation units, IAM chains, and other things probably. 24 Hours of Patch event, obviously, consists of 24 consecutive live webcasts delivered by up-and-coming speakers and experts in the community. To access any of these sessions afterwards, just log on to the 24 Hours of Patch website and you should find them there. My name's Martin Cattrall and I'm MVP and Regional Mentor in the Australasia area. And I've had the good fortune to attend the Patch Summit quite a few times, and it's definitely worth going to. Just a bit of housekeeping. We'll start with technical assistance. If anyone needs any technical assistance during the GoToWebinar, just type in the Q&A pane and I will get to it. There might be a short evaluation at the end of the session, and your feedback's pretty important to us, so please take a moment to complete it. And it'll probably show up on your screen after you close the webinar down. Now, our sponsors are particularly important to us. Without our sponsors, we couldn't do these events. Our main presenting sponsors are Microsoft, Cisco, and Dell Software. In addition to those three fabulous sponsors, we've got another three supporting sponsors: SQL Sentry, HP, and SolarWinds. They all make fabulous software that interacts with SQL Server as well. Now, the Patch Summit, the premier SQL Server event of the year, is coming up towards the end of October. And both myself and I think Brandon will be there, and I'd love to meet all of you. It takes place in Seattle, Washington, 27th of October, and I'll feature over 200 sessions with world-class SQL experts. Planned and presented by the SQL community, for the SQL community. Patch Summit is single-handedly the largest gathering of SQL and BI professionals in the world. We'll have over 5,000 attendees, and it's a great place to network and meet face-to-face with experts, peers, MVPs, and MCMs. Right, so let's move on now to what we're all here for. Our speaker, Brandon Leach. I had the good fortune of meeting Brandon a couple of years ago. I won't say too much about him, but one of the things I find very interesting about him is that he doesn't like tomatoes, but he eats tomato sauce. Apparently, tomato sauce isn't made with real tomatoes, but I'll leave that for another time. So, thanks a lot, and I'll hand over to Brandon now. Cheers. Take it away, Brandon.
All right, thank you so much. So everyone knows a little bit about me quickly, a little bit more. Yes, I will eat ketchup, but most ketchup isn't made with real tomatoes. Also, I am a senior DBA with SurveyMonkey, where we basically help people make better decisions. We have quite an environment at the Monkey. We do about 5,000 transactions a second on just one system alone. So we care a lot about internals and performance and everything you could possibly imagine. So that brings me to today's topic: data pages, allocation units, IAM chains. Oh my! Now, this topic can be a lot to kind of take in at first. You have to learn all these different terms, and they're all interrelated. It's kind of hard to explain one without explaining the other. So, you need to know what allocation units are and how they work with data pages and all this stuff. So I wanted to kind of put together a session that when I initially set out for this about a year ago to kind of make that a little easier for people. So big question is, why should someone care about the internals? Well, the simple matter is it helps you make better decisions. Understanding the internals can affect how you architect something. It can also help you understand how to deal with things like corruption better. So it's got multiple benefits to it. Now, in going through this, there's a few things I want to discuss. This first slide that you see here. This is kind of the anti-agenda. Internals is such a huge topic. We're just going to focus on the storage internals. So we're not going to talk about log internals. There was actually, I believe, a session earlier today on the transaction log and its internals. We're also not going to talk about query processing, how the optimizer takes your query and creates an execution plan, etc. We're going to go a level below that to when the data is actually being retrieved. So memory internals, we're not really going to talk about those either. Again, all these things would be, their own sessions. Well, we also won't cover absolutely every single type of page in a data file. We would be here for days, possibly weeks. However, we're going to cover the absolutely critical pieces. So what we are going to cover is what a database looks like from a storage perspective. In other words, what is the structure of that file on disk? What is a row? What does that look like at that level? What is a data page? What are the different types of storage that SQL Server uses, known as allocation units? We'll also talk about some of the differences between data on disk as a heap, your tables essentially when they're heaps versus clustered indexes. How does that look within the data file? And how do things change? Then we're also going to look at how SQL Server keeps track of what data belongs to what table, object, etc. So let's get started here. Well, we're all familiar with the database in terms of tables that are made up of rows. But the data file is a little different. So our database itself is organized into file groups which contain our data files as well as a file for the transaction log. Now each file group can have one or more data files. This is important because when we start talking about how pages are tracked and we look at contention there, if we have multiple data files in a file group, our data will actually be split across those data files. And it's generally a round-robin algorithm, but preference is given to the data file with the least usage. In other words, the data file that has the least amount of data in it, the smaller one. So there's a couple things that can be beneficial there. And we'll actually talk about, I'll mention a couple trace flags. The first of which is 1117, which will actually make it so that when one data file grows, they all grow evenly. So we're going to focus right now on data files. So what are they made up of? Well, every data file is actually made up of 8K chunks called a page. Now, these pages are generally allocated to a table. They're allocated in groups of 8, also known as an extent. So when SQL Server gets a request for, to allocate more space to, the employee table, it's going to allocate a group of 8 pages, so 64K in size. Well, this is good to know because with data files, you generally want to, at the file system level, have your block size be 64K, and this is why. Well, not all pages are the same. Some pages, in fact, the bulk of the pages will actually hold the data. This is, the page contains the actual rows. But there are other types of pages. There are pages that literally just exist to track which other pages belong to a certain object. Specifically, those are called IAM chains. There are also pages that are used to track what's available for allocation. Those are your GAM and SGAM pages, and we'll get into those a little later. There's a couple special pages, however, that we're going to talk about that exist in your data file, of which there's only one of each of those types for a file. In fact, when we talk about the boot pages in a moment, we'll actually see that that is just one per data file or per database. So let's talk about the file header page. There's only one of these per data file. This page contains information about your growth settings. When you go in there and you change your auto growth settings from 1 megabyte to something actually useful and meaningful for your environment. It also contains an ID that says what file group it's part of and a binding ID to the database. This is so that you can't accidentally attach the wrong file to a different database. But we can actually view this. It's just some special metadata that you can see. There's also the boot page. This is always the 9th page in the data file, and this is something you really don't want to go corrupt. If this goes corrupt, your only option is a full-blown restore operation. Or Paul Randall or Microsoft themselves, I would not recommend you try. But it does contain some interesting info, like the last time DBCC had a good run, meaning the last time that it ran successfully without errors. It also contains a unique identifier for the last full backup. So differentials will actually check against this to make sure that, yeah, I can work with this database if you're doing a restore operation. Also, it'll tell you when the database was created. Again, similar to the file header page, there's actually a dbcc command that allows you to view it directly in a nice table format. You can still use dbcc page, which we'll actually show you in a bit, to view either of these two pages as well. So those are general special pages. Let's get to the meat and potatoes of this presentation. So when we're looking at rows, we typically think of them made up as columns. Well, on disk, it's a bit more complex. There's a lot of things that SQL Server tries to do for optimization. Now, what you see here before you is a general description of what a page looks like. You've got a header, which is about 4 bytes, or which is 4 bytes. You've got then you've got right after that your fixed length columns. These are things like char 5, you know, for zip codes. Your integers, etc. Stuff that's always going to be the same length no matter the value in it. Then on the other side, towards the end, you see we've got our variable offset arrays and our variable length data. Our variable length data is going to be stuff like our varchar columns. And SQL Server does some interesting stuff here. It uses the variable offset array to tell when the next row begins. So the first 2 bytes of the variable offset array are going to be a count of the number of variable length columns. The 2 bytes, every 2 bytes after that is going to be an offset into where we can find that next row, essentially. Basically, where does the row end? So if we don't have variable length columns, we're not going to have a variable offset array, and we certainly won't have any variable length data. So we actually can get a bit of space back for the row if we don't have variable length columns. Now, you would think the same would be true of the null bitmap. But it's not. You're always going to have the null bitmap there, whether or not you've got null columns. So all the null bitmap does is there's 1 bit per column, and it's rounded up, as I note here, to the nearest byte. But it just says if the value is null or not. So SQL Server can look at that, and it can actually say, well, okay, I don't need to go through finding where that column is specifically. I can just check here. Oh, it's null. Great. Or, oh, it's not null. I'll actually look it up. So, when we talk about heaps versus clustered index, we'll get a little more info on this, but let's go to a page. And by the way, folks, I knew you're going to have questions on this, so in a minute after the next slide or two, I will actually stop and take a few questions here so we can dig in a little bit more for you. But let me actually go and talk about a page quickly here. So all our rows, as I mentioned, fit onto 8 kilobyte data pages. And we'll get as many rows on a page as can fit. Now, obviously, the more rows we can fit on a page, the better our table is going to perform. So if we have 10 rows on a page, it's still 8 kilobytes. If we have 1 row on a page, it's still 8 kilobytes. So this is what's called page density. Now, if our page density is very low, we're going to have performance issues. I came across a couple years ago a 400-column table. This was a horrible design. Someone had literally just taken the structure of a file, and rather than go through the process of divvying up that data, normalizing it, making it workable, they just decided to dump the whole thing into one table and call it a day. Well, this table was 400 columns, all varchar 8000, and even worse, they padded the data. So, needless to say, we had a page density of 1. In fact, rows often spilled over. But we'll get to that in a second. And it was painful. You know, just to pull any data out of this table took hours. So what we did was we vertically partitioned. We figured out what columns were not used at all, and we got rid of those. We figured out what columns might be needed at some point, and we moved those to separate tables. Put a view up to combine them if necessary. Then we had our main table became just the most frequently accessed columns. Well, this brought the page density way up, and all of a sudden stuff that was taking, you know, hours, up to 12 in some cases, was suddenly returning in seconds. The reason was we were getting a better page density, so it was able to read more rows per page and get through the table faster. Now, every page has some overhead. We have 96 bytes for the page header. This contains some metadata we'll go through in a moment, all your rows, and then at the bottom, we've got this interesting thing called the slot array. So if you go all the way to the bottom of a page, start at the far right, there's 2 bytes per row. This is an offset telling the SQL Server where within the page the row actually is. Now, this is not ordered by the rows on the page. This is actually, if you've got an index, it's going to be a clustered index. It's going to be ordered by the index. It's another optimization that makes it a little easier for SQL Server to actually find the row it needs much quicker. It's used by binary search, for example, where it will come in, it will look at the middle value in the slot array and say, okay, is the value I'm looking for, it'll look at, let me repeat. So it'll look at that middle value. It'll then go to the row, and it will say, do I have my values? Is this the row I'm looking for? Well, if that ID is higher or lower, it will go to either side. It'll go back to the slot array and cut out half of it. Which half depends on if it's higher or lower. So in that way, it's able to make searching through the page much faster. And so most pages are going to have some free space. When there is no more free space, a new page will be created. If it's a clustered index, you'll see a page split. If it's a heap, it'll just add a new page onto the end, etc. So let's actually look at the structure of a page here. So if I go here, and I want to show you something. So if I rerun this query, so What you see here is I've got a sample database, and I've got a very simple table called employee demo. I've actually used a hidden column known as a virtual column. Phys location, you can see it there between the parentheses, or between the percentage signs. And I've used a function to put that into a readable format. In this case, the function is fn_phys_loc formatter. And so that's my first column of the table. And what we actually see here is what it prints out is, first off, the ID of the file, in this case, file 1 of the database, then the page number, 314, followed by the slot number for that record. So I can use that to actually find the physical location of a specific row. So let's actually go look at page 314. So if I go down here and I run this, now I need to have trace flag 3604 on in order to actually get the full details of this. And I'm also calling dbcc page. Again, this is an undocumented dbcc function. So in this case, its parameters are 0 for the current database, or the ID or name of the database you want to look at. In this case, we're going to use the current database, followed by what we saw in, from the phys_loc virtual column. We're going to use data file 1 with page ID 314. So let me change that to 314. And 3 means we want the full output of the page. So I'm going to bring this up and make it a lot larger for you. So at the top here, this is the output of the page, and what we see right here is the metadata. Down under where it says record attributes, we can see it is a null bitmap and that it has variable columns. We can also see that, if we look right above that to where it says div, we can see that this page has been changed since it was last backed up. So if we do a differential, this page will get backed up. Now, there's a whole bunch of information in here. We can see that we can see a link to the previous page. In this case, it's the first page. We can see just tons and tons of information. Some of this we'll go through a little bit more in depth later, but the important thing to see is I'm going to scroll down here, and we're going to actually see the first slot, slot 0. So we can actually see all our data here. We get a hex dump of it. We see that the row is null bitmap, variable columns. We can see the size in bytes of the record. In this case, it takes up exactly 803 bytes. But just a little more interesting is right below the whole massive dump, puts it into English for us. So we can see that this is the first employee ID 1. We can see some notes, in this case just some junk I threw in there. It's the same notes for everybody. We can see that their manager ID, their first name, etc. So this is an actual data page. If we go down, we'll actually see the second one, and so on and so on. And this goes on for a while, as you can see. So we can actually see all of our rows for that page. So let's go back to our presentation here. And what I'm going to do is I'm going to open it up to questions. So Martin, do we have any at this point?
Yeah, Brandon, we just got two really. The first one is someone's asked, so would you say that the boot page is the most important page in the database?
Well, is it the most important page of the database? More than likely, yes. I mean, every page is technically important because you don't want to lose data. But if your boot page is corrupt, you are not getting your data back. Your database is toast. So yes, absolutely.
Okay, cool for that. And I guess the second one is you talked a bit about page density. Have you got any particular formula on how to calculate page density?
So page density is not going to be perfect. What you can do is you can calculate kind of your minimum and your maximum row sizes, and then figure out how that fits in to your divide that by 8,000, and you'll get an idea of how many rows per page you can actually fit. Okay. It's going to be an estimate.
Okay, but you can only put full rows on a page, is that right?
No, you can put more. You can put as many rows as will fit.
Okay. Yeah.
I mean, sometimes I've seen, thousands of rows on a page. I've seen one row on a page. It's going to fit as many onto a page as it can.
Okay, thanks for that, Brandon. I'll put myself back on mute and I'll keep you posted if more questions come in.
All right, I'll take another break in a little bit. So, all right, so we've talked about your standard data page. So now let's talk a little bit more about things like what happens when a row doesn't fit on a page. What happens when a row flows over, basically? And so this brings up to the topic of allocation units. You see, SQL Server actually has 3 types of storage. The first, in row, is the most common, and it's what we basically just discussed. It's actually the most efficient way to store your data. Then there's what's called large object storage, or LOB. This is very inefficient. When you use varchar max or image or text type columns, this is, or better yet, var binary like SharePoint. This is the type of storage it uses. It uses LOB. And you can think of this as a series of pages. It's almost like, take a squid. It's got tentacles. Each row, for each row that has these var binary columns, like SharePoint does, it's going to have, that column alone is going to have a stream of pages. So if we have a 16 kilobyte Word document that we're storing in the database, well, that's 2 extra pages minimum. So now your row, which may fit on, you know, just, you may be able to get 10 rows on it, on that one page, but now it's got, each row has an additional 2 pages. So if you're reading that column as part of your query, now you've got an extra 20 pages to deal with just from that one column. You know, if you're scanning the entire table. So it's really inefficient. You generally want to avoid those data types when possible. Now, there's also kind of a halfway point for this too, for this stuff too. Something in between row and in between lob. And this is the best name ever. Slob. Because that's kind of what it is. It's similar to large object storage in that, you know, your data will go out to an additional page. However, the benefit to slob over lob is that it will actually share that page. So slob is used for data that's not going to fit neatly into the row. So it'll write it out to an extra page. But say another row overflows as well. Well, that data will actually go to the same page. So these slob pages can actually be shared between rows. And, you know, if that data is not frequently accessed, it might make sense to force it to actually go to slob storage. Well, what'll happen is in your in-row data, it'll actually get a pointer to that slob page. So it'll be able to find it that way. Large object storage, again, you'll have a pointer in the in-row directly to the start of that stream. So slob can actually be good sometimes. Lob you generally really want to avoid. You certainly don't want to store documents in SQL Server. Store a file location. Try not to store your actual documents. So let's talk about some of the differences between heaps and clustered indexes. So whenever you create a table, initially it's a heap. It's basically just a continuous stream of pages, but I like to think of it as my floor if I didn't have a hamper. Or okay, let me rephrase that. My floor before my wife, you know, kind of kicks me a little bit and says, pick up the pile of clothes. So everything's just in a giant pile on the floor. It just ends up wherever. It's really fast because, well, you're just throwing stuff at it. So inserts are ridiculously fast. But, you know, if you had to find anything in it, it would be tough. You know, pick up this, pick up that. You know, if I just have an unorganized bookshelf would be another example. I just stuck a book anywhere. Finding that right book, the one that I want, would be next to impossible. It would take eternity. Well, There are also some things you should know about heaps. First off, because there's no cluster, there's no index, there's no key on them. The SQL Server will actually assign an 8-byte identifier. So you're actually paying a penalty there off the bat in terms of storage, because you've got an additional 8 bytes for every single row. Now, 8 bytes might not sound like much in today's world, but think about how many rows you have in some of your tables, and you see how, that adds up. So the other thing that happens with a row is that the rows can move. If you update a row and it's no longer going to fit there, well, SQL Server will put a pointer where the row was, and it'll actually move that row to a new location. So that pointer will just contain the location of the new, it'll contain the new location of the row. So the other thing that happens is, when you delete data, it creates gaps. Well, inserts can come in, they can fill that gap. Like I said, it will literally be really fast for inserts because it's just going to put it anywhere it can fit. However, these gaps, if you've got a lot of deletes, you're going to start to see performance issues after a little while because your data is a little more spread out. Reads also hurt because now to find anything, like I mentioned, you gotta go through the whole thing. So that brings us to clustered indexes. So they've got a slightly different structure on disk. They don't have that 8-byte RID. So they don't have that extra hidden column. And so when you convert a table from a heap to a clustered index, you are getting a lot of benefits in a lot of cases. In most cases, to be honest. So the data is actually organized by the columns that are part of the clustering key there. So, if you're going one column, say employee ID, like my demo table there, well, now a new record comes in. What happens? Well, what's going to happen is SQL Server is going to look at that. It's going to go through the index and say, okay, I need to stick this here in the third page for this table. Well, if there's space in that third page, great. The row will get added there. If there's not, then we're going to end up with a page split where SQL Server will take the page, cut it in two, and then insert our row. Now, lots of page splits is not that great of a thing, but page splits in general, that's a normal operation. You can tweak this with fill factor, but generally I wouldn't recommend you do that unless you see an issue. You generally don't want. So, before I move on to the next section, Martin, do we have any more questions?
There's no questions come through at the minute, Brandon.
Okay.
If anything comes through, I'll get your attention somehow. You're doing great, mate. We're very interested.
All right. So we're getting to we're getting close to the last section here. So in fact, this is the last section. So let's talk about how objects and their pages are tracked. Well, obviously, if we've got all these data pages, we have to have some way of saying this page is part of this object. The way SQL Server does that is through what's called an index allocation map. And so these are special pages within the database that actually help track, what extents are allocated to an object. And remember, earlier I said SQL Server allocates extents, a group of 8 kilobyte pages. So the index allocation map, we call that an IAM page for short, and they cover 4 gigabytes worth of extents. So every 4 gigs, you're going to see an IAM page. You're also going to see that these IAM pages are chained together. They contain pointers to the previous page and to the next page. This helps SQL Server when it's trying to find certain pages. It can go forwards or backwards depending on what it needs to do. So it's also important to note that each allocation unit for a table has its own IAM chain. What that means is that you're going to have 3 IAM chains for each table minimum. Now, if you're using partitioning, each partition will have its own allocation units, and thus each partition will have 3 IAM chains. So these things, you can get a lot of these things. You can actually use dbccin, which will list out the pages for the table, including the IAM chains. It's another undocumented procedure, and I've got an example of it. Do not use this on a production system. Do not. It will incur a high amount of load. So do not, under any circumstances, run that on a production system. But if you want to explore in your own isolated environment, great. So there are also pages that exist to specifically track what can be allocated. And this brings us up into a couple points. So we have what are called GAM pages, the global allocation map. You will have one of these every 4 gigabytes within the file. In fact, a GAM page is one of the first pages you will find in the data file. It has to be, because everything is extents. So it's a bitmap. So you'll see a bunch of zeros and ones when you look at it. 0 means it's not available for allocation, meaning it's already been allocated. 1 means it's already been, that extent has already been assigned to an object. Now, these pages see heavy use, especially in TempDB. You'll hear of GAM and SGAM contention. This is why it's a really good idea to have multiple data files for your database. How many? Well, that depends. You'll hear advice of, the general advice is 1 per logical core up to 8. Don't add more than 8 unless you absolutely need to. Oftentimes, unless you've got a really big system, I start off with 4. That's usually enough. But this helps you reduce GAM contention because your data is split out over multiple files. You've got multiple GAM pages. It means that they're going to see less contention, and you'll likely get better performance. Absolutely do this for TempDB immediately. If you've got one data file for TempDB, you need to go back and you need to fix that. It makes a big difference. Now, there's another side to this. There's a special type of extent called a mixed extent. A mixed extent is one that actually it's allocated to multiple objects. And this happens when you first create a table. When you first create a table, your its first allocation will be a mixed extent. This comes from way back when disk space was a huge bottleneck. So today it's not needed, and you can actually shut this off. If you shut this off, it's trace flag 1118. To be honest, it's harmless. This is one of those, I rarely, if ever, would recommend that you just enable a trace flag. This is one of the few that absolutely enable it. As always, though, test. This will actually give you a good boost in TempDB performance, because what will happen is you'll no longer, all those temp tables that get created, well, they're not getting a mixed extent anymore. They're getting a full-blown extent. And so SGAM pages are used to track what extents are mixed. So again, it also covers 4 gigabytes worth of extent. So when you enable that trace flag, you are making SGAM pages pretty much useless. Value of 0 means it's allocated to one object or has no unallocated pages. Value of 1 means that a page in that specific extent is available for allocation. So yes, interesting there. Now, since we have pretty much reached the end, do we have any last questions about tracking, about allocation, or about how pages are tracked in IAM chains, etc.?
Yeah, there was one question that came through before, Brandon, when you were talking about clustered indexes.
Yep.
So should we then decrease density fill factor for the clustered index so that new rows don't reorganize to pages?
So that is very much an it depends. Generally, I would say not to mess with fill factor unless page splits become a problem. Because you're hurting yourself. The trade-off with fill factor is you are specifically lowering your page density in exchange for less page splits. And page splits aren't really a bad thing. They happen normally, but it's important to get as many rows on a page as you can. So only mess with fill factor when you've done extensive testing and you feel it's worth the trade-off.
Okay, thanks for that. So is the fill factor something that you change at the table or index level or at the database level?
You specify it at the index level. When you're creating your clustered index or your non-clustered index, you use the with fill factor equals option.
All right. Okay. Well, there's no more questions come through there, so yeah.
All right. Well, we're good on timing then.
Okay, no, that's pretty good. That's pretty good, Brandon. Really, really enjoyable, really informative. I learned a fair bit there myself. So all that really remains for me to do now is to thank Brandon and thank our audience. And in addition, I'd like to thank our presenting sponsors, Microsoft, Cisco, and Dell. Obviously, without them, it wouldn't be possible. And in addition, I'd also like to thank our support sponsors, SQL Sentry, HP, and SolarWinds. There's another session up due after this. I think maybe data development and unit testing. Do you know, Brandon?
Database development and unit testing.
Yep. So that'll be on the line very shortly, unless there's any final questions coming through, which I don't see at the minute. But we'll be here for a couple of minutes at least, I think. I just thank you all again for your time, and hopefully see you at the PASS Summit. If you do happen to be there and you want to meet myself, Brandon, or anyone else, we're a friendly bunch there, so do come by, say hello. So we'll either see you there on Twitter or other social media. So thanks everyone, and see you later.
Thank you.